In the last video, we opened a pull request to close an issue for the DMD compiler, but I didn't go into much depth about the actual code change I made. It was really simple, but in general, finding the right code change is the hard part of fixing a bug. So this video aims to help you find your footing in the DMD codebase. And it's a very large one. The DMD compiler and the runtime combined add up to about 500,000 lines of code. So where do you begin trying to understand how it all works? When I first tried to get familiar with the code, I started reading source files, like a book. Just pick a file and start reading from top to bottom. This did give me an impression of what the code was like. However, I don't know what your current impression is, but if you think you're gonna see modern, idiomatic, straightforward, well-documented D code, well, one of those is right. Apart from a first impression, this isn't a very effective strategy. Reading code like that gets boring. Your brain doesn't work like that. You don't just read code and memcopy it into your memory and then you know it. You need context and understanding to remember it. So I'm going to cover 4 aspects that I think will help you make effective changes to the DMD code. A low-level understanding of D, a high-level understanding of the compiler, the code style of the compiler, by which I don't mean braces and indentation and stuff. Instead, think about common functions, common types, and code patterns. And finally, a deep understanding of the compiler code. Starting with a low-level understanding of D. In order to understand the D compiler, you also need to understand the D language, of course. You can get this from using the language, reading the specification, or other books and articles about D. If you just started using the D language, I wouldn't recommend already looking into the compiler. But apart from knowing all the high-level semantics of D features, it's also useful to understand how language features work under the hood. For example, an integer array under the hood is a pair of a pointer and a length, similar to this struct I defined here. Similarly, throwing exceptions and creating new classes gets lowered to calls to functions implemented in the runtime. So how do you get a low-level understanding of the features? One resource I recommend for this is Walter Bright's DConf Online 2020 talk, A Spoonful of Sugar, which explains how higher-level ideas translate to low-level operations in D. For a more hands-on approach, you can inspect the abstract syntax tree before code generation with the VCG-AST flag, or using the AST button on run.dlang.io. In this example, I have a for each statement and a scope exit statement with a function call with an arithmetic expression, and when I press the AST button, it shows the AST before code generation, where the for each is lowered to a traditional for loop, the scope exit statement is lowered to a try finally, and the expressions are constant folded into single integers. And this can also help you give an insight in how high-level ideas are transformed into lower-level constructs. Similarly, you can inspect the generated assembly by the compiler with the -vasm switch, or using a site like the Godbolt Compiler Explorer. On this website you can type D code and see the generated assembly output. Here I'm using the example of throwing an exception again, and you can see the call to the D runtime function D new class and the throw dwarf. This does require a bit of familiarity with assembly, but if you have trouble with a certain instruction on this site, you can simply hover over it and get a summary of what it does, which is nice. Moving on to the next aspect, a high-level understanding of the compiler. At the most basic level, it consists of a front end which does D-specific analysis and the back end which does language-agnostic code generation, and it's usually taken from a C compiler. In the case of DMD, it uses the Digital Mars C compiler's backend. Within the front end and back end, there are several stages, some of which are lexing, parsing, and semantic analysis. If you want to get more familiar with those, any book or tutorial about compilers will do, but if you want something D-specific, I recommend watching Walter's DConf 2016 talk. Being from 2016, some parts are outdated, such as the directory structure, which is different now, and the inlining pass is being moved from the front end to the back end. The rest of the info still applies today, so it's definitely a recommended watch. Next up, code style. Again, I don't mean the syntax, but rather common functions, data structures, and code patterns used throughout DMD. Because even with the best high-level understanding of all compiler passes, at some point if you want to write the code, you need to know how the code is being written. So what are the types associated with each phase? The driver reads a source file and converts it to UTF-8 text, represented by an array of characters, and then the lexer splits it up into tokens, so it's useful to know the definition of the token struct. The parser reads tokens and converts it into an abstract syntax tree, which uses classes and inheritance for all the nodes. The base class for an AST node is called AST node. Now, semantic analysis does tree rewriting, but it still uses the AST node type for it. It's just that certain nodes and subtrees are converted to new nodes and subtrees. The glue layer converts the code generation AST into a form that the backend understands. DMD, using the DMC backend, uses the elim struct for this, which is a struct-based tree type with a tagged union. But other compilers, such as LDC and GDC, using LLVM or GCC intermediate representation for the backend, convert it to that. The code generator, after optional optimization, will eventually turn it into machine code, a binary file with target-specific instructions. So where do you find these parts in the source code? For that, I recommend the README in the source tree. So going from the root of the DMD repository to compiler, source, DMD, and then scrolling down to the README, you can see a document describing the directory structure and all the files related to each compiler phase. We were talking just now about AST nodes. Here you can see a link to astnode.d, which defines the abstract class AST node. And for example, in expression.d and statement.d, you can find definitions of concrete AST nodes, deriving from the AST node base class. One unfortunate thing you'll have to deal with is incidental complexity. The compiler is a large complex program partly because D is a large complex language, but there's also other factors which make it more complex than necessary. For example, the age. DMD was written by Walter Bright starting in 1999, but some of the code in there dates back to his earlier compilers from the 1980s. And even though it's all been translated to D as of 5 years ago, a lot of old C-isms remain in there. For example, the use of printf style format strings and zero terminated strings, bit twiddling using bitwise operations to manipulate bit fields, and old style capitalized enum constants. There have been efforts to refactor and modernize the codebase, but there's still just a lot of technical debt. Another source of complexity is the C++ interface. The GDC and LDC compilers use the same front-end code as DMD, but they are written in C++ and need to access DMD's data structures from C++. Therefore, a lot of functions and data structures are annotated with extern C++. Also, root object is used as a top-level base class instead of the regular object, because it needs to be accessed from C++. C++ has trouble interfacing with D arrays, so a custom template array type is used in DMD instead of regular arrays. And when extern C++ data structures or functions are changed in D, the corresponding definition in the .h header files also needs to be updated. Naming things is also a source of incidental complexity. D syntax needs to be named using identifier characters only, and the compiler is in this awkward position where it needs to refer to its own keywords. So an if token is defined in the toc enum as if underscore to make it a valid identifier. Each part of an expression needs to have its own name. The plus operator gets turned into an add expression, but it could have also been called a plus expression or a sum expression. So all this compiler jargon is something you have to learn, because you don't have to deal with this as a user of the language. Similarly, types have names which you aren't used to as a language user, such as a D array, short for dynamic array, or an int32 for 32-bit integer, which is simply called int in the D language. Going the other way isn't always obvious either, because names can sometimes evolve. For example, typeinfo invariant has nothing to do with invariants as in contract programming, but are just the old name for immutable, which still hangs around in the compiler internals. And would you guess that a compile statement refers to a string mix-in the position of a statement? The in-out type qualifier internally is currently still called wild, as in wildcard, which is also confusing. So this is something you have to deal with when reading compiler source code. Even though you should be able to deduce what all these names mean with a little bit of browsing and searching in the source code, it will slow you down when you see all these names and have to check every time what they refer to. But once you overcome this hurdle, it gets a lot easier to get the final part, a deep understanding of the code. This is what we set out to accomplish. Without it, you can still fix a spelling mistake in an error message or something, but it is necessary to make non-trivial changes. But it's also the hardest and most time-consuming compared to the other 3 points I discussed so far. The good news is, you don't need it for the entire codebase. While I do think it's important to have a holistic, high-level view of the entire compiler, you only need a deep understanding of the parts in which you're interested. If you only want to make a change in the lexer, you don't also need a deep understanding of the parser and semantic analysis. And similarly, for making a change in semantic analysis, you don't need to know the lexer and parser inside out. You can just assume they work and produce the data structures that you're familiar with, and work from there. And if you start fixing different kinds of bugs, you'll slowly but surely understand more and more parts of the compiler. And getting a deep understanding of parts of the code is a lot easier when you already have a basis of a low-level understanding of the D language, a high-level understanding of the compiler, and an understanding of common code style and patterns and functions and types, which is why I provided resources for that in this video. So finally, what resources are there to get a better deep understanding of parts of the codebase? There's very few videos or books about this because it's very niche and technical and ever-changing, but what you can do is look at the pull request queue, find a pull request implementing a similar feature or doing a similar bug fix to what you want to do. Here I am in the DMD repository again, going to pull requests, and for example, this is a pull request deprecating a feature. And if you go to the code changes, you can find an example of everything needed to deprecate something, such as a changelog entry, a comment showing when to remove the feature, the deprecation function with a message, test cases over here being adapted, etc. Another thing you can do is step through the code with a debugger. I don't have a demo for this ready, and I usually don't do this myself, but I've heard from other programmers that this is their preferred way of exploring an unfamiliar codebase and learning things about it. And finally, just start making simple changes and work your way up from there, because in the end, you'll learn the best by doing. For a final resource, I'll leave you with the contributing guide, which will also tell you a lot of helpful stuff. And if you think there's anything missing in here, or you just have any questions in general, one thing you can do is go to the discussions tab and open a question there. And that concludes this video. I know I haven't gone into much specifics yet, but there's just so much to cover. So stay tuned for the next video. Until then, see you next time.